All right, we're ready to go now. Sorry, folks, for the delay. Just a reminder, last day we looked at the concept, we revisited the concept of friction. We said that friction could be calculated. It depended on two things: how sticky or slippery two surfaces were in relation to each other. We called that the coefficient of friction, symbol mu. A low mu close to zero meant really slippery. A higher mu closer to one meant really grippy. We also said it depended on the normal force. In fact, this was an equation a lot of you still remembered from last year. Friction was equal to mu times the normal force. I don't know the normal force. We often had to figure out the normal force from a good free body diagram. We looked at a couple of thought puzzles. We did a couple of questions, and we got right to here. So read along with me. There are actually two types of friction. There can be friction on an object when it's at rest, because those microscopic hills and valleys, they kind of lock up and they settle into each other. So if I push on this desk right now, well, you know what? We got a good thought puzzle. The force of friction on an object at rest is called static friction. Static means not moving or unchanging. So here's our thought puzzle. Suppose I pull on a desk with a force of 2 newtons and it does not move. So I'm pulling with about 2 newtons right now. The desk is not moving. Which of the following statements is true? A, static friction is bigger than 2 newtons. B, static friction is exactly 2 newtons. C, static friction is less than 2 newtons. Or D, there is no static friction. You know what? I think we're going to vote again. How high you hold your hand up is how sure you are of the answer. So if I pull on a desk with 2 newtons and the desk doesn't move, which of the following statements is correct? Who says, oh, obviously static friction is bigger than 2 newtons. That's why it's not moving. Answer is A. A. I got 2. Just 2. Static friction is exactly 2 newtons. Ooh, 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, Sean just joined in as well. So you know what? We have our famous lots minus 2. Why does the answer have to be B? Why can't A or C or D be correct, Gerard? First of all, let's not, yeah, good. I put the word moving in here on purpose to mess with you. Newton's laws tell us nothing about moving. What do they tell us about, Gerard? Accelerating. If the forces weren't balanced, the desk would have to accelerate. In other words, if A was correct, yeah, it would suddenly, when I let go, it would have to be accelerating in the opposite direction. Okay. If C was correct, it would have to be accelerating towards me. If D was correct, well, that's like ice. It would absolutely accelerate towards me. Uh, ooh, Gerard, which of Newton's laws could I use or did I use in that answer? The one that talks about if forces are balanced, an object won't accelerate. Okay. So if you knew that, you could say Newton's first, and I would live with that. Or you could say forces must, well, you could say this: A equals 0, so forces must be balanced. And I would live with that as well. The net force is 0. Because again, I've told you, you don't need to memorize, Alejandro, which one of Newton's laws is which one, but you can if you want to as shorthand. So we talked about this a bit last year, and it was a little confusing. We're going to talk about it a bit this year, but then I'll give you a bit of a hint. Static friction is the force that varies from 0 when we're not pushing on it. So right now, how big is the force of friction on that desk there? 0. How do I know? Because there's nothing pushing or pulling in the opposite direction. Forces must be balanced. If I pull with 5 newtons, how big will static friction be if the desk isn't moving? 5 newtons. Let's use my desk up here. If I pull with 10 newtons and the desk isn't moving, how big must static friction be exactly in the opposite direction? What if I pull with 12.3? 12.3. What if the biggest static friction can be is 20 and I pull with 20.1? Okay. If you want to calculate static friction, turns out, you may have noticed this, if you're ever trying to slide something really heavy across the floor, getting it moving is tougher than keeping it moving. You actually have to push a little bit harder to get it moving, and then it'll just start to slide on its own a little easier. And that's because technically, Ashton, there's two coefficients of friction. There is a static coefficient of friction, and there is a kinetic coefficient of friction. The kinetic one, Oliver, is when it's moving. It's usually a little bit less than the static one. Um, why? Well, we talked about how friction was microscopic hills and valleys between two surfaces connecting and grabbing as the objects slide together. Jeremy, you may have noticed if you're ever on a really, really bumpy, gravelly road that has lots of potholes, if you go really slowly, you feel every single pothole. But you can go at about maybe 15 kilometers per hour, and the truck tires will actually not fall all the way into the pothole. They'll skip across, they'll catch the front edge. It's still bumpy, but it's smoother than going really, really slow. Probably there's something similar happening at the molecular level. When you start it sliding, no longer do the bumps fall all the way into the valley. They're just catching the front as you're sliding it along. And so we have a coefficient of friction, a static coefficient of friction, a little higher, and a coefficient of friction, a kinetic coefficient of friction, once it starts to move. Friction is still mu times the normal force, but let me give you an example of where the difference would occur. Did I show you the 0 to 100 kilometers per hour in less than a second video last class? Okay, make sure I don't forget. An object sits on a surface. The static coefficient of friction maximum is 0.3. But once it starts to move, the kinetic coefficient of friction is going to be 0.25. A says, determine the force required to move the object. To move the object, I've got to pull harder than static friction. This is a job for a free body diagram. I'm going to do my free body diagram right up here because I know I'm going to need more room to write underneath. So imagine the object sitting on the floor. What are the forces acting on it? Get the obvious one. Which way? What else? Which way? Bigger, smaller, or the same size as mg? I think the same size still. We're going to have an F applied, and we're going to have friction. A asks, determine the force required to move the object. I think the object will move when F applied exactly equals friction, but this is going to be static friction, friction when it's at rest. Technically, Timmer, actually, it's going to start to move when F applied is 0.00001 newtons larger than friction, but the tipping point is right when they're equal. So friction is what times what? It's mu times the normal force. Have we started sliding yet, Maya, or not? In A, we haven't. So it's going to be the static coefficient of friction times the normal force. Maya, what's the static coefficient of friction that they gave me in this question? Mu s. Yep. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Which one? Yeah. So it's going to be 0.3 times 5 times 9.8. How hard do we need to pull to get this thing to start to slide in the first place? What do you get? Maya, what'd you get? Oh, reaching for the calculator now. Everyone's all tired first thing in the morning. 14.7 units, newtons. So then B asks, if I pull with 10 newtons, what's the acceleration? You can do this in your head without writing anything down. Ryan, as a number exactly, what's the, yeah, A is going to be 0 because we're not pulling enough. And in fact, friction isn't going to be 14.7. It's going to be exactly 10 newtons. What if I pull with 12 newtons? What will the acceleration be? 0. How big will friction be? 12. Ah, in part C, how hard am I pulling, Nate? Will it slide now? Will it accelerate now? Yeah. So now we're going to have a different equation for part C. Now F applied is winning. So it's going to be who's winning? F applied minus who's losing? Friction. What's that going to equal? MA. But friction is not 14.7. In fact, the first thing it says is actually find the force of friction. Friction now is going to be mu kinetic times the normal force because it started to slide, and kinetic means moving. What's the kinetic coefficient of friction? Yeah, it's going to be 0.25 times mg. 0.25 times 5 times 9.8. What do you get? Sorry? 12.25? Okay. And I'll carry that on my calculator. So now, Nate, how would I find the acceleration? Well, if it's F applied minus friction equals MA, I'm going to delete this. Make sure I don't forget to show you the video, but I need more writing room. It's going to be A equals F applied minus friction divided by the mass. Right, divide by M. What was F applied in part C? 20. What was friction, Jeremy, now that it started to move? Divided by the mass was 5. I might do this in my head. 20 take away 12 is 8. It's going to be 7.75. Divide by 5. What's a good way to do that? Divide by 10 and then double it. So it's going to be 0.775 times 2. It's going to be 1.4, 1.5. 1.575. I don't know. What'd you get? 1.55. Dueck. Meters per second squared. I always talk about that because years ago I had a student ask me, Mr. Dueck, how come when I start to slide something, I have to push harder to get it moving, but then I can ease up a little bit? They'd noticed that. So this is the explanation. Having said that, we're going to pretend, Ashton, that there's only one type of coefficient of friction. There's one question in the homework that's very similar to the one we just did. But on a test, if I give you a coefficient of friction, Andrew, you can assume it's mu kinetic or mu static or whichever one you need at that point in time. I'm not going to distinguish between the two of them. Okay? What's your homework? You're getting there. Number 1 is good. 2 is good. 3 is good. 4 is good. 5 is good, and 6 is good. And I made a video solution for 4, 5, and 6 because they're all sort of similar questions. If you're stuck, your hint for 4, 5, and 6 is they're so easy that they're tough. Good free body diagram. Number 7, this is just like the example that we did. Has 2 different coefficients of friction. We're going to skip 8. 9 is good. 10 is good. We're going to skip 11. 12 is good. 13 is good. 14 is good. Skip 15. Skip 16, but 17 is good. Pause the video.